I'll begin this afternoon session with a brief introduction. Welcome to the Canadian Institute of Forestry's National Electronic Lecture Program. My name is Sharon Young, and I will be hosting today's session. Today is Tuesday, January 27th, 2026, and this is the first session in the e-lecture series entitled Applied Research Perspectives Across the Canadian Forest Service. The series is a collaborative effort coordinated between the Canadian Forest Service and the Canadian Council of Forest Ministers. The CIF-IFC is very pleased to collaborate and host these webinars. For today's session, we are pleased to welcome Mathieu Fortin, Juha Metsaranta, Chris Hennigar, Mihai Voicu, and Gilson, who will present a strategic plan for the advancement of national climate-sensitive growth and yield modeling in Canada. To start us off, Mathieu Fortin is a research scientist in forest biometrics at the Laurentian Forestry Centre. He earned his PhD from Laval University and joined the Canadian Forest Service in 2019. His research focuses on stochastic growth models, upscaling techniques, and statistical estimation with a strong interest in implementing models into software. Next, Juha Metsaranta is a research scientist with the Canadian Forest Service, where he studies the interaction between forest carbon dynamics and climate change. His work supports Canada's national forest carbon monitoring, accounting, and reporting system. Joining him, Chris Hennigar brings over 20 years of experience across the forest sector, including private consulting, collaborative research, and 10 years with the New Brunswick Department of Natural Resources. He joined the Canadian Forest Service at Atlantic Forestry Centre in January 2025 and has been working toward the development of climate-sensitive forest growth and yield models for Canada. We also have Mihai Voicu, a forest carbon modeler specializing in Canada's boreal ecosystems. His work focuses on carbon budgets, growth and yield, and regeneration. At Canadian Forest Service, he leads data-driven initiatives that support national forest carbon monitoring and reporting. Last but not least, Gilson currently works on the carbon accounting team, where he develops climate-sensitive models based on tree ring data. His research interests include modeling and effects of climate on tree growth and yield, and investing in new statistical methods for developing forest models. With that, I will now pass it over to Mathieu to begin today's e-lecture session.
First of all, on behalf of my co-authors, I would like to thank you for the invitation to talk about this strategic plan. This initiative started in 2020. I'll give a bit of a story, of its history later on. But I just want to mention that it's a much larger team than than the co-authors of this presentation. I'll provide you with a bit of context, and then we'll move on to how we are implementing the strategic plan for the advancement of national climate-sensitive growth and yield modeling in Canada. So, as you all know, the climate is changing. This figure is from the sixth assessment report of the IPCC and shows different scenarios of climate warming over the 21st century. The Paris Agreement aims at keeping us close to this dark blue line. So we don't want, according to the Paris Agreement, we don't want to cross this threshold of +2 degrees compared to the pre-industrial period. However, there is some evidence that we're actually not controlling that much our emissions, and we'll probably end up somewhere a little bit higher than 2 degrees at the end of the 21st century. And this has tremendous impact on forests. We just have to think about species distribution. Species distribution are conditioned by the weather, and if you increase temperature, it makes some habitats unsuitable and makes new habitats suitable for species. So we have to take this into account. The forest dynamics are changing. Why is it important? So in forestry, we focus on sustainable forest management. In many jurisdictions, it's actually enforced by a law. And to do that, we really need projections of future forests, and we need reliable projections. And so far, our models have been working under the assumption that the climate would be constant in the future. So what we took as granted is no longer true. The climate is going to affect how forest develops in the future. And that means there's going to be impact on how tree grows, how they survive, and eventually what is the composition of the new trees in any particular location. So our models, the traditional yield curves that we've been using for so long, is no longer reliable for long-term projections. So we need to take this into account. In 2023, we ran a couple of queries on Web of Science, which is an engine that makes it possible to extract from the literature, the available literature, scientific literature, I mean, a number of studies with certain characteristics. So if you look for empirical models here, we can see that from the 90s, for example, up to the 2020s, there's been an increasing number of articles that were published in the scientific literature. And when you look at those that take into account the climate, I'm sorry, here you see that. Okay. We can see that there's an increasing trend, but still there's only, in 2020, there was only 30% of those papers published that would be climate sensitive. So there is a huge gap. We're still publishing empirical models. Empirical models mean those models that rely on statistical relationships. So they're closely tied to the data and regular inventory data or training data. So there is a tremendous gap here. We still have 70% of those models that we publish that are not climate sensitive. And when we look at process-based model focusing on the process behind growth, like photosynthesis, respiration, we see that the number of papers that we publish every year might be less, but there is a major proportion of them, over 75% in 2020, of those published papers, they were actually climate sensitive models. So there are room for improvement in both types of model. One thing for sure, at the moment in Canada, most forest management relies on empirical models. So those statistical models based on statistical relationship. So there's a gap here, and it really motivated us to start this initiative in 2020. So just to the next slide. So we started this initiative in 2020, just before the pandemic. We had a first CFS internal workshop where we discussed climate sensitive models. At that time, there was the carbon accounting team. So the team at NRCan, who's in charge of making projections of the carbon balance of our forest in the future and see how forests can mitigate climate change. The thing is that they were using yield curves that were climate insensitive. So that has been a constant criticism on the methodology. And there was really a need. The team really expressed a need for climate sensitive models that would feed their carbon budget model they use. So we created an internal committee, and we're meeting every month or so to decide to take actions and decide what we're going to do about it. In 2021, we ran a survey of climate-sensitive growth and yield model efforts in provinces, the different provinces and territories, to see what was the current status of where we were at that time and what could be done to improve our capacity. In 2021, we ran a second internal workshop, and we started also to have those regular meetings every 4 months or so with provinces and territories, where the provincial and territorial initiatives could be showcased, and so that the other provinces and territories would know, okay, this is going on in Ontario, this is going on in Northwest Territories, and so on. In the meantime, there was the strategic plan that was designed and finally adopted by the Canadian Council of Forest Ministers of Forest. And in 2025, we had again a workshop led by CFS. So this strategic plan has 5 goals, and I will skip the first two because they're rather high level, and I want to talk more about goal 3, 4, and 5. So goal 3 is really about developing new components or adapting existing one to make them climate sensitive and to be able to produce climate sensitive projections. So that's the end goal, being able to produce the climate sensitive projections. Goal 4 is about transfer knowledge with provinces and territories, industrial partners as well. And goal 5 is really to engage with provinces and territories. And we've been very successful, I think, with goal 5. To start collaborating with provinces. We are in a moment, either at the federal level or provincial level, the resources are stretched. You all know, you've seen the news, we are undergoing there's a workforce readjustment going on here, throughout the federal government. So the capacity is limited. We need to collaborate to make sure that we're going to be successful, and we start to do that. So the strategic plan has been accepted in 2024, and there's a link if you ever get access to this presentation. And I think it's going to be accessible probably on the website. There's this hyperlink giving you access to on the website of the Canadian Council or Forest Ministers. You get access to the strategy, the document. I'll pass it over to Juha for the next slides.
Thanks, Matthew. So just another thing that we did, so Matthew described sort of our, the research outputs are on this topic are increasing over time. So what we did as a team, another thing we did as a team in concert with that strategic plan is that we actually, we did kind of what I would call a comprehensive technical review paper of all of the growth and yield models and some process models with potential applications in forestry, forest management, and looked at these models in terms of their current implementation of climate sensitivity, and as well we looked at it, and we looked at the literature and did some thinking about what types of data that would be or methods that would be helpful or required if we were going to make models more climate sensitive, and then an overview of where we think advancements could be made. And we'll get into this later, but we're sort of our activities that we're doing now are responding to some of the results of our literature review. And there's a link to that. Some of you may have read this already, but there's a link to the paper that came out in the Forestry Chronicle about this. Next slide. Okay, so in our classification of Canada's current models, we sort of put them into 4 classes here. The first one being that the model doesn't have any climate inputs. So it assumes a static climate. And we also classified some models as indirectly climate sensitive. So what this means is that there are some components of the model that are expressed as a function of climate variables. So a very common one would be, for example, that the site index part of the growth and yield model would have climate variables. So you could modulate the site index as a function of a future projection under a climate scenario. Then there were also some models which had what we would call average climate sensitivity. So this would be, there may be some component, for example, in a vegetation type or something like that includes something like a 30-year climate normal in the equation in that particular component of the model. And then the fourth type, which there weren't any models in this category that, at least in the traditional growth and yield models, but this would be models which are annually climate sensitive. So this would be a model component that relies on an annual or intra-annual climate variable. So this would do something like you would enter a drought event, for example, using a moisture index of some kind, and the model's prediction would reduce, say, the volume increment for that year. Those kinds of there were no models that were like that. Next slide. Yeah, so this is basically a summary. So out of the 15 empirical models that we reviewed that are kind of, the models that are commonly used in Canada, there's 9 that were not sensitive to climate at all, and 6 were already modified to include either indirect or average sensitivity. And of the 7 sort of process or hybrid models that had some application or use in forestry research, all of those had the capacity to have annual climate sensitivity. Next slide. So as I said, so out of one of the results of that process, we made some suggestions for where we could research activities that would be fruitful in terms of improving the situation. And so this is a summary of what the areas of work that we're currently doing. So we have some work that's looking at integrating information from tree rings. There's a national site productivity project that's remote sensing based. We have some work on incorporating genetics from various trials. And then we have an overall team that's working on growth and yield models and software. So we're going to go over a little bit about each of those topics now, but I'll start with the tree rings component here. Next slide, Matthew. So on that front, so another project that we're working on in the Canadian Forest Service is we have this CFS trend database where we're compiling all of the ring width observations from increment core data that have been collected in Canada. And this is an ongoing initiative that we're working on. There's a separate working group, but I think we have these numbers for sites and cores are a little bit higher now, but this is somewhere where we're collaborating with a number of provinces to do things like measure their permanent sample plot increment cores and implement and incorporate that into this database. Next slide. So what we want to do with that is to sort of leverage the tree core data in order to be able to create these annually sensitive diameter increment models that we can then potentially, we're looking at this as a research project, to potentially incorporate annual sensitivity by substituting the sort of traditional diameter increment model that's parameterized from PSP, periodic PSP data, with one that's uses the annual increments from tree cores. Yes, that's one of the projects that we're working on. Next slide. I think it's over to you, Matthew.
Thank you, Juha. So the second topic we're focusing on is really to take advantage or to leverage remotely sensed data in different ways. So one of them is really to work on multiple acquisitions in order to derive the height increment. So that's what you can see here in the above panels. And eventually this can be modeled in order to get growth rate indices. And those growth rate indices could serve as input in our climate sensitive models, and they could eventually be expressed also in terms of climate. So this is what we're trying to do right now to integrate remotely sensed products with growth and yield models and to make all this climate sensitive. Another option too with remotely sensed data is to build models directly from remote sensing data. So an example is here given on the left-hand side. So Piotr Tompalski published last year. I want to say this year, I haven't shipped to 2026 apparently, where he basically modeled the above ground biomass for different species throughout Canada. There's also something we worked on a couple of years ago we wanted to develop yield curves at the pixel level. So it means having a yield curve for each pixel that is 30 meter by 30 meters in the field. So those are products that we're working on. And eventually we want to reach a full integration of remotely sensed data and growth models. In terms of genetics too, there's an idea. We're working mostly on what we call in science space for time assumption. So it means that when we assume that the tree, let's say a black spruce right now in the boreal forest, the black spruce in 20 years from now will grow with the climate we observe in 20 years like the black spruce that is growing further south. So for example, if we really, the temperature increase a lot, those black spruce here, let's say around Ottawa, there are not many of them, but there are some, so would grow like the black spruce we might have in Tennessee, but I don't know if the distribution extends so further south at that point. But that's the thing we're assuming. We're assuming that trees will grow in the future like they grow in the south. And we don't take into account the genetic adjustment here. Some populations might be more adapted or less adapted. So this team really focused on genetics. And the idea at first is to create a national database from progeny trials and to check out the gain in terms of height growth, diameter growth, volume growth, and so on. So there is a ongoing collaboration with the provinces and territories here to gather the data and to see how those adjustment factors could be implemented in their models. So there would be those adjusting yield curves, for example, given what we've seen in the progeny trials. So far, with we can see that the different data have been collected and put in the national database, data from BC, Alberta, Nova Scotia, and their ongoing work and data sharing agreement that will probably signed in the future to integrate progeny trials from the other provinces into this database. In terms of growth and yield modelings, we have ongoing initiatives with provinces and territories, especially Ontario and Quebec, to further develop to develop new model components that are fully climate sensitive, and also working on a model that some of you might know. It's called the Mixed Wood Growth Model. It's usually called by its acronym MGM. And that model covers the prairies, provinces, Yukon, Northwestern Territory, and Northern BC. So we're working with some people to improve the components of this model and to make them more climate sensitive. So those models are all tree-level models. And normally what you have in tree-level models, you have different sub-models accounting for mortality, survivor growth, and recruitment. So what is complex here is to make all of those components climate sensitive. And so we're working on those three main components. We're testing climate variables to see, okay, what is the trend given the current climate and how we could expand that using the space for time assumption. And we have surprising results. So we could think that the mean temperature from June to August, if it becomes too hot, for example, you would think that it would be detrimental to survival. But for northern boreal species, if you increase the temperature in the summer, you could think that that was a limiting factor. So if I increase it, I'm going to get a better growth, better survival. So here on this graph, you have the 5-year probability of mortality. And what we can see would actually the opposite. So our trembling aspen, which is a boreal species, or characteristic of the boreal forest here, if you increase the temperature, apparently it's detrimental to survival. So we get a higher probability of mortality. And we would have thought that with sugar maple, the red line here, we would have got a pattern like this, that we increase the temperature, it becomes too hot for sugar maple, but no, apparently it decreases the mortality, so it's beneficial for survival. So the response to climate is very species specific and also region specifics. That makes it a little bit complicated. And for that, we need very large data sets. So that brings me to the next slide. So we haven't been working only on growth and yield modeling, but also on data, collecting data and building an international database of permanent plots. So international, it's because it's not only Canadian data we're interested in, but also those in the US, because the climate in 50 years from now in Canada might look like the US right now. So yeah, that's the space for time assumption I was talking about. So if you look at the different provinces in the US, they have this FIA inventory, which is homogeneous throughout the US, or well, let's say, not entirely homogeneous, but much more homogeneous than what we have in Canada. In Canada, depending on the provinces and territories, we have different designs. So could have things very simple as in Quebec, permanent plots, 2 plots on the cruise line. They are 500 meters apart. So that's quite easy to implement, well, to gather the data and build a database from the data. But when you want to put that in the same database as what you have in BC, for example. In BC, you have many different designs. So you can have clusters of 5 plots with subplots within the plots and microplots and so on. So you need to really define many tables and build clear relationships between those tables. And Chris Hennigar has been working really hard over the last year on designing a structure and database structure that could make it possible to host all the data we find in Canada, all the designs we find in Canada, as well as in the US. And I would say that we've been really successful. So we have a database of permanent sample plot, and we have over 150,000 plots, and 70% of them have been measured at least twice. And you can see here the distribution. We covered the whole Canada here. Well, it's a bit less dense in the prairies, but in the US, we also have a large density of plots. So, and all this together in the same database so that we're going to be able to do something that we could not even think of 20 years ago when I started in my career, is to build a national allometric relationship that will be climate sensitive. So Jessica Chavez, who's working with us in our teams at the moment, she's fitting eye diameter relationships that are climate sensitive for Canada. And we're also working on other growth and yield models that are national. So there was one published in 2009, but it was mainly, at that time, the database was heavily trended towards Quebec data because they were readily available. So that national model is, I would say, a bit biased towards Quebec. And now we have this huge database. We can revisit this model and fit it for whole Canada. And we can even think of a national tree level model. So a model where we would grow every single tree in a plot, but we could apply it throughout Canada. And that's an initiative that we're going to start this year, this national tree level model. So, we've been talking a lot about, on the forefronts, we've been talking about what we've done and what we will do in the near future. But I want now to bring you to something really new. So things have changed a lot over the last 25 years. So people used to work much more in silo before, not because they were, close-minded, but more because the tools for collaborating were not that easily accessible. And now we're working under different conditions. Just with OneDrive, we can easily share files, make work jointly on a PowerPoint presentation like we did this morning, with Juha and Chris. So there's all those tools that we can leverage to improve our capacity, and we have a greater accessibility to decision support software, greater access to those collaborative development tools. So you might have heard of Git. So Git is a versioning system. So it means that it's used in software development, but we can use it for whatever you want. So if you're working on something with collaborators, you can make changes, commit those changes, and eventually you can go back to an early version if you find that you made a wrong decision and you just want to roll back to in the past to a version that was more stable, for example. So we can take advantage of that. And there's even the infrastructure that is available on the web. So if you know GitHub or GitLab, those are two infrastructures available where they could host Git repositories. So you can create many of them. That's what we're doing right now. We're using we're developing codes, we're putting in under Git system, and we're putting those pieces of code on GitHub. And we have many of them that are actually open access. So you can get access to them and you can start collaborate with people that. So it happens, for example, the other day, someone just pointed me on GitHub, okay, there is a bug in your script here. Here is the solution. You could fix it that way. And so it really facilitates the collaboration with internal and external collaborators. And there's also something that has changed a lot over the last 25 years. People are much more proficient in coding. So you might know the R project. So it's become a standard in the in science. People use R and they develop packages for example, to process remotely sensitive data, or to give access to an allometric relationship, or even to get access to a growth model. So this is a very convenient way of sending a growth model, a climate-sensitive growth model, to someone. There's also those object-oriented languages that can be developed, and they're much faster than R, Java, and C#, and also some Visual Basic. So those are languages we're working with to develop tools and to make them accessible on GitHub to our collaborators and even to at large for anyone. So an example of that is Chris has been working a lot on processing the data and being able to retrieve the data from the provincial and territorial databases and format them and put them into an SQLite database. So we've built pipelines to do that. So we have pipelines for each jurisdiction of province, and we just gather the data, process them, and put them into a single database. And that's very efficient, actually. So those pipelines can be accessed on GitHub. So those are not public, but if you're interested in collaborating, please reach out to us and we'll show you how. And Chris will address that in a presentation in 3 weeks from now. So he's been working, for example, with New Brunswick to develop this sort of pipeline relying on R. It's driven by R, but in the background, in the back end, you have SQLite requests that are made and from which you extract the data and you format your SQLite database. And he's also working on an application to really identify outliers and measurement errors in the data. It's called PlotCop. So we're really at that stage now. We have our big database and we're going to process all the data through PlotCop to identify those outliers and measurement errors. We're also building a national system of growth and yield projections. We want a system that's scalable. At the moment, most of our growth models apply at the tree and plot level, and the reason is quite simple. The data that is used to fit those models is actually data measured in plots or data measured at a tree level. So those models, as such, do apply at that scale, but we need them for forest management units. So we need to do this sort of upscaling. So we're developing techniques to do that as well. And we try to have most of our applications, and especially this national system of growth yield projection, user-friendly. So you might not want to access a complex tree-level model and provide a complete tree list, first of all, because you don't have it wall-to-wall. And when you have it, you need to format it and then pass it to the model. It's somewhat complicated. What people used to work with in forest management is a set of yield curves, of growth curves like this. So we're trying to make those growth curves as those are meta models. Actually, we use a complex model here to fit those meta models, and those meta models are those we make available on this national system of growth and yield projections. And this is where it gets really tricky. We want a modular system. So we have OSM, the OpenStem model that applies in New Brunswick that Chris has been working on for quite some time. It's coded in C#. And then you have FVS, whose core is coded in Fortin. And then we have some libraries and other models running in Java. And finally, we have a weather generator whose core is coded in C++. So you can see the diversity of programming languages that we have here, and we want this to interact. So it's called in the technical term, it's called interoperability. So we want to be able from OSM to call biosim to retrieve climate data, for example, do the same with FVS. And when we have a new version, we want to be able to remove OSM and put the new version of OSM. So all of this would be modular. So to do that, we're using web APIs. So a web API is a client-server approach, and this has become really popular over the last 20 years, I'd say. So you can download the OSM version on your system and use it as a desktop app, but then you will need to make the connection and so on, and it might not be integrated in your workflow. If you're working in forest management, you would like to produce yield curves from that. So another approach is to host OSM on a server and to use this client-server approach. Client-server, what is it? The client is you on your computer. You're going to send a request to the server and say, hey, buddy, I would need a yield projection from OSM with these data, these parameters, let's say. At this point, the server cannot do anything. The server just receives a string and doesn't know what to do with it. So what we need is an extra layer of code. And that extra layer of code that would actually process or parse the request so that it becomes understandable by OSM. And in turn, it will also adapt the output to make that understandable for the client is called the web API. So basically the request comes in, it goes into the web API digests it, send it to OSM, OSM runs the simulation and send back the result to the client. And if you wonder, you're using web APIs all the time. Every time you Google something, your client is actually your browser on your machine. And when you Google API programming, for example, you're going to see the URL is going to change here. That's the request you're sending to google.com to a web API called search. And all those here are the parameters. Now, if we would like to make sure that you will never use a web API, I would tell you, okay, you want to use OSM model, just enter this very long string in your browser and you're going to get the answer. So the very long string should contain the tree, tree information, diameters, height, and so on. So that's a very long string and you don't want to do that, then you won't be able to use it. But what we can do is to provide you with clients for the web API. So clients is a little piece of software that is going to compute this long string for you, send it to the web API and retrieve the results. And this is what we have. So an example of that is in our package called OSM Web API for R. And this R package can be installed quite easily in R. You can just send your tree list to OSM, to the server. The server is going to send it to the web API. Web API is going to process it, send it back, and you're going to get the answer on your end, in your R environment on your system. So those are tools that we're developing. At the moment, we've developed web APIs for OSM, Artemis. Natura has been implemented as a web API by the provincial government in Artemis too, also by collaborators, Hugues Power and Isabelle Auger, who are working for the Forest Research Branch for the Ministry of Natural Resources and Forests in Quebec. We also have FVS BC, and we're currently working on adapting NGM and creating a web API for it. And eventually, we will be able to cover whole Canada. So we intend to have this national model, but also all those provincial models from which we'll be able to make projections. And the interesting thing behind this is eventually we're going to be able to make projections with more than one model for a particular context, just like what they do at the IPCC. So those climate projections were based on 30 models. So why can't we do the same in forestry? So we could at least use two or three models eventually. So this idea of having an ensemble of models behind our projections is really the center of our efforts. We're also developing dynamic libraries. So creating an OSM library, a allometry library that will be used in PlotCub. Those allometric relationships could also be used somewhere else. So we're working to make sure that things are partable or can be extracted of our software. We also have a similar library in Java, CFS Forest Tools. So you want to use a volume equation, for example, you could do that in R using this library. So I'm going to skip these two here. Just want to get to our conclusions. So fundamentally, this initiative has been really fostering a collaboration with provinces and territories. So we've been developing climate-sensitive growth and yield models with provinces using different approaches and different sources of data, and especially trying to leverage remotely sensed data so that we could extend the coverage of our model, apply them wall to wall. We're also developing software solutions because it's really in goal 4 of our strategy. There's this knowledge transfer. It has to go through those software solutions. Everyone works in computer nowadays, so we need to provide pieces of code, small applications that make it possible to run growth and yield simulations and obtain in the end climate sensitive projections. That was also it was also the opportunity for collaborating, but using those collaborative tools in the sense that we're now collaborating on different repositories in GitHub. There are some where provincial partners are in charge and we're just supporting them or contributing to those repositories. There are repositories where CFS is really leading them, and our territorial and provincial partners are also collaborating and providing pieces of code and finding bugs, fixing them. And so together we're kind of stronger than working isolated. So the next slide is really a self-promotion one. So if you are interested in this topic, or I should say these topics, the four e-lecture, the next 4 ones are those on February 3rd up to February 24th are about those topics. So if you're interested in remote sensing on February 3rd, Joan White and I think Piotr Tempolsky and Jose Riofrio will address this topic in detail. Training applications with Liam and Juha will be on February 10th. Chris Hennigar will talk more in details of the tree database that we've been working on, this international database. And finally, on February 24th, more detailed examples of climate sensitivity integration and growth and yield models. So as I said in the introduction, that's a huge team. So at CFS, there are many people contributing to this initiative. I won't name them all, and also provinces and territory. And I apologize in advance if you don't find your name here and it was overlooked and you're collaborating with us. Please just remind me through an email, and I'll make sure to update the slide to make sure that your name is there. And I want also to outline the contribution of Don Robinson, who's been working on FVS, provided advice on how we could implement FVS into a web API, and Jean-François Lavoie, who's working with us on a continuous basis as a consultant with the implementation of web APIs. And finally, thanks for your attention.
Thank you, Mathieu, Juha, Chris, Mihai, and Liam. That was a great presentation. Now let's move on to the Q&A session. All right, seems like we have one question in the Q&A pod, and I will read it out. How are we relying on AI to interpret data and develop relationships from tree data that our small brains cannot see or imagine?
I can start.
Go ahead.
We don't do that, actually. And the reason is quite simple. It's because the relationship that we're fitting, the statistical models, there's a strong emphasis on error uncertainty assessment. So we prefer to rely on parametric methods. But that said, we rely on AI, especially to develop our tools, the documentation of our software solutions, because it's really time consuming and the AI does a pretty good job. So it's really, I'm not saying that using AI is not bad. We're using it, but for really the core of our relationships, we're not using it right now.
I would just add to that. It's pretty slippery when people say AI, what that means. I think a lot of times people say AI, and that might refer to what just a couple years ago would have fallen into the realm of machine learning. And I think some of what we do might use techniques that were considered machine learning, but I think it's hard to know when people talk about AI whether they mean something that could be machine learning or whether they're specifically talking about sort of large language models and generative AI. And that's really not something we're using except for documentation, as Mathieu mentioned.
Yeah, I would just say that, like, okay, so we describe these data sets that we're putting together, and they seem big for our area of work, but in reality, these are, if you look at like the data that are available for, like, I don't know, let's say consumer preference research or something like that, we have tiny data sets relative to a lot of like other people out there, and you know, like, even though, yeah, like the PSP data set may have millions of trees, but that's still, you know, we don't have billions of trees. We don't have tens of billions of trees like you would in some other contexts.
So the first question in the Q&A pod is, what climate variables are important predictor of tree growth? Probably you might have sent a mixed response of climate variable based on geography. For example, temperature might have negative impact on southern Canada and may have positive impact in northern Canada. Could you add a few words on this?
Yeah, that's a very good question. And we realized that when we work at the provincial or territorial level. So we could expect, for example, in exactly what you said, that the response is actually, if you look at the species distribution, it should be somewhat bell-shaped, you know, very, very small at both edge of the distribution, and having a more positive effect in the center of your distribution. So those climate variables, they do not have purely linear effects, so that's very unlikely. The problem is that when you're working at a provincial level, you could cover only a part of the distribution, and so you might have, you know, the part that is increasing of the relationship, or the part that is, you know, going down, or only the top, so that would be flat and you would see no effect. So that's precisely the reason why we're now working with this international database, because we have a much broader geographical extent, and we cover, in many cases, we cover the whole distribution of the species. So we have the complete relationship. And what are the climate variables? So it's hard to tell. There's always, you know, temperature-related climate variables that we use in models. Also, humidity-related variables that drive the growth, basically. And so you can use, I tend to use degree days because I find it really relevant and closely tied. But in many, you know, many other people would use the average temperature of summer. And the example I showed you in the presentation was actually with the mean summer temperature. So there is no, I don't think that we should be too stiff on that and say, okay, too strict on that and say, okay, we should all use degree days. The most important thing is to have some biological explanation behind your data. Okay, that's my opinion, and I will let the other people to reply.
I would echo what Mathieu said in a specific development of some yielders for small trees in Northwest Territories. We found out that growing degree days and potential annual evapotranspiration were the best climate variables. So just as one particular case when that worked.
Thank you, Mihai. Now we're going to move on to the next question. What is the strategic advantage of a client-server design? What functionality does this offer that is not provided by, for example, an entirely local workstation solution?
The advantage of having a client-server design is if you want people to use your application and you send them a package like what was done before in the 90s and the early 2000s, so you would download a desktop application. So as a developer, you have to maintain those different versions over time, and you don't know who's using what. With a client-server approach, everybody's using the same version, the one on the server. So it's much easier in terms of maintenance, and you have a closer link with the whole community. So that's much more practical. It's less practical if you have very intense job to run, and we see that with Biosim. We have a web API implementing Biosim. So if you run something really demanding, it's going to take more time to run it on the web API. It's going to take significantly more time to run it compared to a desktop application. So that's a trade-off. But personally, for the maintenance, I prefer the web, the client server setup.
The only other thing I'd suggest maybe would be that for researchers and folks like the carbon accounting team, where they've got to access all these different models across Canada, if we had a common platform that was server-based where we could access these models through R, that has some real advantages for those researchers and the carbon accounting team, and even the public, which a lot of these provincial models are very difficult to use. They just require a lot of background knowledge, a lot of inputs, and if we can kind of provide something that the general public could maybe get a hold of and use, and have a common platform across Canada for doing that, that would be advantageous.
Thank you, Chris. Moving on to the next question. How does biomass production in Canada compare to Europe? From the slide you shared, the total species biomass over 150 years in Canada appears lower than what is typically observed in Europe.
Yeah, that's true. Go ahead.
Did we show that? I don't know if we showed that, Mathieu.
I think there was this metamodel curve.
Oh, okay.
Okay.
Yeah.
It's just an example from Chibougamau, so it's in the boreal forest. So of course it does not produce a lot compared to what we have in Europe. That said, the productivity in southern Quebec, Ontario, is maybe not as good as in Europe, but comparable, I'd say. But as soon as you get into the boreal forest, you should not expect productivity comparable to what you have in Scandinavian countries, for example. And there's also a management effect. So the forests are much more intensively managed in Europe compared to what we have in Canada. So remember, foresters coming from Europe, they look at our forests and they say, you're wasting so much wood. Those dead trees, we're just taking them out and we process them into planks and boards, and you're just wasting them in the forest. It's to say that the philosophy is really different. The access is different too.
Thank you, Mathieu and Chris. Moving on to the next question. Can we borrow from work being carried out for agriculture crops? What approach are other countries, jurisdictions taking on forest modeling? Can we learn or steal from them?
I think, we've borrowed sort of long-term from the work being carried out at agricultural crops, but the problem with forests and trees is that it's a very different world, and we have to make projections further out. Like with agricultural crops, maybe you're fine with a 1-year projection, and forestry, 40 years isn't really that long. But, there's sort of general things like work on photosynthesis or C3 photosynthesis parameterizations from agricultural work have bled into forestry, especially into process-based models. But we are certainly looking at the approaches that other countries and other jurisdictions are taking. And I think we're incorporating knowledge from the reviews we've done of what's going on sort of all over the world into our own planning for forest models. And I think certainly I'll be talking about that in a couple weeks with the tree ring stuff, but I think there's a plenty of sort of initiatives all over the globe to look at incorporating climate into forest models that are kind of taking a fairly similar approach here, looking at sort of an empirical model and trying to figure out how climate can be put into it.
So moving on to the next question. Does these models also incorporate biotic effects of climate change, such as increases in forest pathogens and pests?
So we can do it, but in an indirect manner. So what we can do in our models, for example, in the growth component or in the survival component, and even in the recruitment component, is to account for past disturbances. So we're not projecting when it's going to happen or how frequent they are, but we can, for example, account for the increase in mortality due to the spruce budworm outbreak in the 70s and in the 80s in Eastern Canada, for example. Okay, so we can do that. And once we have the model that account for potential insect outbreak, now simulating how frequent will be those outbreaks in the future and how intense they will be is another story. But that said, the model can take it. So it can take it as a factor provided by another model. So if we have those projections in the future, we can use those as input in our models to simulate more frequent spruce budworm outbreaks, for example.
Yeah, and you look at things like emerald ash borer making its way into Eastern Canada, and our data isn't going to allow us to build a model that is going to just magically incorporate that into our tree level models. It's more of a something that we probably incorporate in after the fact and adjust our mortality rates in ash accordingly. Or if we saw a new pest coming into our environment, we would try to make some estimates around, what kind of effects on tree growth and survival that insect or pathogen is going to have, and then try to make those changes at the tree level in these models. And some of these models are pretty good at making those changes quite easily. So that's typically how we've approached things. Endemic pests tend to be incorporated to a certain extent already in the PSP data. So those impacts tend to have already been considered, but certainly epidemic outbreaks and new pests are something that we need to consider above and beyond what we fitted in these growth models.
Thank you, Chris and Matthew. Moving on to the last question. Are you considering the effect of increases in atmospheric carbon dioxide and carbon dioxide fertilization on tree growth in the recent times and potentially in the future?
It's a tricky one. I'm an empirical modeler because I work mostly in statistics. So I don't do it in my empirical models because it's correlated with many other climate variables. So it's hard to distinguish what comes from the CO2 fertilization or from the warmer temperature. I think though that it can be considered, and I think in most cases it's considered through process-based model. And maybe it was not obvious in the presentation, but we want to have, when I said ensembles of models, we don't have any inclination towards empirical or process-based models. We think that each model brings a part of the answer and is worth being compared with the others. So far, we do not have any process-based model into our national system. But if someone wants to join in, a process-based modeler wants to join in and collaborate on the integration of their process-based models into that platform, we would really be glad to do that.
Since we now have detailed forest resource maps, wouldn't it be better to develop a new model that directly integrates these maps to develop climate-sensitive models that can be parameterized for different species and site conditions, rather than just translating and combining existing ones?
Yeah, I think that, that's part of the intent. One is to combine existing models and translating them into a common platform, but we're certainly developing new models as well. And Mathieu pointed out a stand level model that we're trying to build right now, a stand level increment model. And starting this year, we're looking at building a national tree level growth model. So that will be using, it's really going to be a brand new model.
So maybe I'll just add a couple of things here. So in the broader world of science, one of the things that that's coming out is, so in any given situation, when we have, say, several potential models that could be used in the context of forecasting for answering a specific question, often what's coming out as the most useful strategy is to sort of combine multiple approaches. So it would be, if you have right now, what we would do in a growth modeling context in forest management is we would run a projection of growth for one model. But that's in the research area, in modeling in general, that's sort of counter to what's currently the best practice that's being suggested, which would be to say that, okay, we need to develop, say, 3 models or 4 models that have slightly different data sets or data supports or processes included with mathematical formulations, all of which could be kind of somehow considered, I guess, scientifically supported. And then you would use those in an ensemble to inform your decision making. So that's kind of like, so there's no reason to choose one over the other. We can explore the development of multiple approaches. And Mathieu sort of alluded to this, where this is how, in fact, when we make projections of the future climate, this is how it's done. There's many, I don't know, I think it's somewhere in the order of 30-ish climate models that underlie the IPCC assessment report projections of the future climate. So that's an example of something we're trying to get to. We don't consider it a problem when there's more than one model, or in fact several models that could be applied. It's rather like an opportunity to kind of better understand maybe our structural uncertainty and things like that, if that makes sense to everyone.
Thank you, Juha. All right, before we wrap up, I'd like to remind everyone that this webinar has been recorded and the recording will soon be available on the CIF Open Access e-lecture webpage. If you have any further questions after this webinar, please feel free to reach out or join us in the future webinars. We'd be happy to connect you with our speakers. All right, now I would like to bring this session to a close. Thank you all for participating in our CIF electronic lectures. And once again, thank you very much to Mathieu, Juha, Chris, Mihai, and Liam for the great presentation and answering all the questions. Bye, everyone.
Thank you very much. Bye-bye.